Now today's session we will discuss the properties of an ideal switch. Before I begin today's session, just a very quick recap of whatever we have been seeing in the previous two sessions. First and foremost, we had tried to understand the essence of power electronics. The essence of power electronics is switching at high frequencies. In one word, if you want to tell, that is the essence. Now, we switch at high frequencies because we want to reduce the size of the inductors and transformers. Why do we do this? Because we want to control and coordinate electric power and how do we do this? We are going to use semiconductor devices. Now, why are we using semiconductor devices? Of course, along with inductors and capacitors. Why should we use inductors and capacitors instead of resistor? The idea is, if we want to control and coordinate electric power, or in other words, if we want to process electric power, convert electric power in one form to another form, then that conversion, the power conversion process, must happen efficiently. Resistor being a dissipative element, we wish to minimize the effect of resistance as far as possible. Ideally, we don't want any resistance, so that power conversion, again, ideally power conversion is going to be 100% efficient. But practically, there will be some stray resistance. Therefore, that resistance should be as minimum as possible. That's all. So to put in a nutshell, the essence of power electronics is about controlling and coordinating electric power using semiconductor devices along with energy storage elements, namely inductors and capacitors. This process is done at high switching frequencies of the switches, of course, so that the size of the magnetic elements, that is inductors and transformers, are going to be reduced. This is one main point which we had been discussing for the past 2 days. The other aspects involved around the applications. Power electronics is actually finding application in domestic applications like LED lamps, fluorescent lamps. Nowadays we have inverter air conditioners. Whatever appliance you take, whatever domestic appliance you name it, that the first stage is going to be the rectifier stage. Internal processing is done in DC form. Please remember that as well. The internal processing, power processing, is happening only in DC form. Final stage will be, it could be AC because the appliance works in AC, majority of appliances, unless and until there are going to be some DC native loads like LED lamps, electric vehicles. They need DC, they work in DC form, therefore they are called as native DC loads. So, but for such native DC loads, all other appliances, the processing is happening in DC form. The final output may be in AC form. Because we are using AC predominantly, the input is in AC form. So this is the broad understanding that you should have. I was talking about domestic application, I do know that. The other application of power electronics is industrial drives, where we use huge induction motors, very big DC motors or synchronous motors for controlling the speed of the drive. There again, power converters play a very, very important role. And then in modern day fields or modern day research aspects like power systems, renewable energy systems, smart grid, they are actually thriving because of power electronics and its associated control. That was the second aspect which we were discussing. And in between, I had mentioned about the various revolutions of power electronics. Actually, first revolution started with the invention of thyristors, and then came second revolution was about power converters, various power converters using those thyristors. Third revolution was about modern day devices. Modern day would mean those days, 1980s, 1990s. IGBTs, MOSFETs, high power devices, they again revolutionized the way power conversion was taking place. That was the third revolution of power electronics. And then came the control strategy, fuzzy logic, artificial intelligence based control of industrial drives. They actually revolutionized the way efficient drives were being put into use in various industries. That was the fourth revolution of power electronics. And then came intelligent power modules along with various controls. So fifth and sixth revolution of power electronics is all about modern day power electronics, wherein we have compact, I was mentioning this term, custom made power converter. All right. So we give, we meaning the user tells one particular application, and then power electronics is going to play an important role for that particular application. That's all. It's not going to be generic anymore. Rather, it is going to be specific. Fine. Please understand, the application or the power converter could be specific, but then the way manufacturing happens, manufacturing of devices, manufacturing of components, manufacturing of modules, they are actually generic in nature. And that is the third point which we were discussing. Now, because I said generic, I'll give you an example. I tried to relate the previous session also. Towards the end of the previous session, I showed you one white color module. I called it as inverter module, semicron inverter power module. Now that is the generic modular based power converters, which are being used nowadays. Fine. Please try to understand the difference. The module is not application specific. Module is generic. Fine. So manufacturing is generic. But if you take a particular application, let's take single phase grid connected inverter, then all that one needs to do is take that module, depending on the power level, take that particular module, use it for your application. So the application is going to be custom made, specific, user specific power converter. Whereas the components which are being used, the elements which are being used to construct that power converter, they will be generic. They are generic. Fine. So this is the trend that is going on. And incidentally, I was mentioning power is being processed in DC form. In fact, if you are fortunate enough, you will have a course on smart grid. That is an elective course, and you will have 2 more electives on power converters and switch mode power supplies as well. If you are really interested, you can take up that course, those 3 courses actually, and then you will be able to correlate how electrical energy is being used, or people are thinking of using electrical energy in DC form, DC microgrids, DC form. So that is actually playing a big role, or that is one form in which people are thinking of using that. In fact, all of you might be knowing the very big, famous war on electric currents, AC versus DC. Do you all know that? Yes. War on DC? Sorry, war on electric currents. Rohit Das?
Yeah. Edison.
Yes, okay. What was it all about?
Edison told that DC was better, but Tesla told that AC was better.
And how long did that fight carry on?
That I'm not sure, sir.
Okay, fine, excellent. You try to, if this is for everybody. If you are really interested, you should actually know this, the history of AC. Just put war on currents, war on AC currents. You will get wonderful information about how 2 giants, Edison and Tesla, they were fighting for decades together, and then finally AC won, Tesla won, because in those days would mean 1798, 1800s. So in those days, power conversion was very, very difficult because semiconductor devices were not available those days. Fine, that is why people started using electrical energy in AC form, whereas nowadays that's not the case. The first, even yesterday I demonstrated, the first stage is rectification, and then the processing today I mentioned is happening in DC form. So nowadays things are, the war has actually begun again, it has resumed. Fine. But now you can't find one particular winner. There won't be any one particular winner, let's say DC or AC. That's not going to be the case. In fact, in another 10 years, 20 years time, both are expected to coexist. They have their own advantages and disadvantages, therefore they have to coexist. Something like what I keep repeating this. the application, the advent of power electronics has actually helped power system engineers. Though initially they were fighting with each other. Reason being, you will understand this a little while later also. Reason being, when power electronic converters came into existence, the beautiful sine wave that was in place till that time in power systems, that totally was disrupted. Pure power system specialists, purists, they even till date, they don't like power electronics because power electronics is causing distortion. It's not disruption, distortion. Distortion in quality of waveform. Fine. So they didn't accept power electronics initially, power system specialists. Later on, they found out that power electronics, the solution again lies in power electronics. There are devices what are called as custom power devices, flexible AC transmission systems, capital FACTS, flexible AC transmission systems. So the solution to that distortion came from power electronics. It is like you can take a thorn using another thorn. It is something like that. In Tamil, we have a cliche. Mulla mulla la dhaan edukkanum. I do not know how many of you would understand. The rough translation is what I said earlier. You can take out a thorn using another thorn only, or another needle. That's all. Fine. So that is then power system specialists started accepting power electronics, and now it is continuing as a good happy married life. They are together, power system and power electronics people. All right. So this is the gist that we have been discussing in the past two sessions to be precise. Fine. Now I would like to pause for 1 or 2 minutes, then take up any queries. In case you have some doubts, please go ahead. Okay, so without wasting much time, I would like to pass on to today's session. Please understand, it is just a standing instruction. Whenever you have a doubt, please feel free to interrupt. Please feel free. You can unmute and you can put up your doubt. Chat box, I may miss out that chat box, whatever you type in chat box. So feel free to interrupt. No issues at all. Absolutely no problem. So take it as a standing instruction. And similarly, my voice, audio quality, internet connection, anything, if there is an issue, please feel free to indicate that to me. Okay, so I have shared my screen. And I hope you are seeing a screen with some graph. Are you able to see this?
Yes, sir.
Yes.
Yes, sir.
Great, good. Then we are good to go. Okay. Now, as I was mentioning earlier, today's objective is to understand the essence of a switch. So what are going to be the beneficial properties of a switch or the ideal characteristics of a switch? I will just write it as characteristics of a switch. We will try to understand this and then we will list the characteristics one by one. Characteristics of an ideal switch. What are the most preferred characteristics? We will try to understand them. Now, the graph that I have shown here, of course, I haven't marked the X and Y axis. I will mark the X axis as voltage across the switch. I will indicate as VSW. And along the Y axis, I have plotted current through the switch, which I will indicate as ISW. And I have a family of curves. Now, these set of curves, they are obtained for a particular control variable. I will just indicate this as for various. I will just put a control variable with an arrow mark with the variable one. Control. I am varying this control. What does it mean? In case I have a 3-terminal, have you come across BJTs, bipolar junction transistors?
Yes, sir.
Yes, sir.
Can you name the terminals of a BJT?
Collector, emitter, and base.
Base. Okay. NPN transistor, what are the terminals? PNP transistor, what are the terminals?
Gate, drain, and
NPN transistor, PNP
no,
transistor. Again, only BJT. So will they be different?
No, it is same only.
No,
It is
sir.
Same only, sir.
Yeah, it is same. It is same. No doubt. It is same. Don't take much time. Just to review certain things I'm asking. That's all. So if you take a BJT, you have three terminals: collector, emitter, and base. Among these three terminals, two will be power terminals, which means you apply the input voltage. One terminal will be the control terminal, wherein when you are able to vary that control terminal, control parameter, the VI characteristics can be varied. This is the essence of, or this is the principle based on which we identify the terminals as, we categorize the terminals as power terminals and control terminal, power terminals and control terminal. Now in a BJT, can you identify power terminals and control terminal? Two terminals across which we apply input, one terminal which is used for controlling.
There is base the controlling input.
Base is the control. Good.
And emitter and collector
Which
will be
means
the
remaining two terminals will be the power terminals. Why are you people reluctant? Please don't be reluctant. See, this is just an assessment. In case you have some other opinion, please tell. You tell collector, base, emitter. You feel free to open out and speak. Only then you will understand. Okay, don't feel shy, and somehow you have to unmute and have this habit of responding. Only then things will be easier. Okay, so if you take a BJT, especially BJT specifically, this V switch will be voltage across the collector emitter. I am writing it in a very small font size deliberately, whereas the current will be the collector current. I hope you can see this. And control is going to be base current for various values of base current. Let's say IBN, and this is going to be IB1, IB2. This is the family of characteristics. Have you come across this characteristics? VCE versus IC for various IB. Have you come across this characteristics? Yes or no? Louder, please. Yes or no? Yes. Okay.
Yes, sir.
Yes, fine. Now, I'll stick on to the same BJT, same characteristics. I will now try to shade some portion, and then I'll try to find out how do you name this region? Do you have a particular name for this region where IC is 0? Do you have a name for this region which I have indicated, hash? This region, which I am highlighting now. Do you have a name for this?
Cutoff region.
Very good.
Cutoff.
Good. Cutoff region. Okay. Now I'll indicate the other region as well. And do you have a name for this region?
saturation region.
Saturation region.
A bit louder. Yeah, saturation region. I did hear it clearly this time. Good. So this region is the saturation region. I will name it here. Saturation region.
Saturation.
Good. Correct one. Cutoff and saturation. There is one more region. Do you recollect that? One more region. Where will it be?
Active region.
Active region. Excellent. Where will it be located? You can only tell. You can't draw. Just try to elaborate. Where will it be located? Meaning closer to the y-axis, closer to the x-axis, top, bottom, middle, something like that.
Somewhat in the middle.
Top.
Top. Okay.
Part of middle, sir.
Middle.
You mean here? This is top.
Middle, sir.
Middle portion. So this is not correct.
Middle push.
Middle portion, which means I'll try to circle and put a vowel, and then this region is going to be the active region. Now, very good. Nice that you are able to recollect. Now, what is our intention? Our intention is to find out the characteristics of an ideal switch. For that, we should understand what is switching. What do you understand by the term switching? Please feel free to answer. Switching, what do you mean?
On and off.
On and off, that's all. Okay. So when the switch is on, what can you expect? What parameter, electrical parameter is going to be important? When the switch is off, what electrical parameter will be important?
Current, sir.
Good. I think I interrupted. Can you repeat?
Current, sir.
During?
Current, sir.
Yeah, current during which state?
On state.
On state, you are thinking about current through the switch.
Saturation.
Whereas during, yes, saturation region. Excellent. So off state, you will be talking about or thinking about off state voltage across the switch. That's all. Fine. Which means when the switch is on, when I will use some other color. When the switch is on, I will write it as when switch is on, then you will have current flowing through the switch. This is not a rocket science, but then you need to understand this. Current flows through it. Now that current which is flowing, we have indicated as ISW. What will happen to voltage across this switch when the switch is on? Ideally,
it will be 0.
But louder, you are correct.
0.
0. That's all. Ideal switch, you should not have any voltage across the switch when the switch is on. Because we have mentioned ideally, ideal switch. Ideally, what should be the current handling capability of the switch? Ideally. Meaning, would you
Sir, can you
restrict the
repeat,
current?
sir?
Yes, I will. In an ideal switch, voltage across the switch is 0 during on state. Whereas current through the switch should be some value. In an ideal switch, what will be that value? That is my question. Is there any restriction? 5 ampere, 10 ampere, 100 ampere, 1000 ampere, ideal switch.
Infinite.
That's all. Exactly.
Infinite.
Good. Really good. Very good. So in an ideal switch, current should be, or the current handling capability of the switch, current handling capability of the switch, of the ideal switch should be infinite. Voltage across the switch during on state should be 0. These are two characteristics of an ideal switch. Fine. Infinite current handling capability during on state. 0 voltage across the switch during on state. Now, did you understand this? Any doubts? On state, did you understand?
Yes, sir.
Yes, sir.
Good.
Yes, sir.
Good. Now, let us try to find out what happens when the switch is off. Pretty easy, because you have understood on state. This you will be able to answer. Even you were answering that, you were only answering the previous questions. Fine. Now, during off state, what do you think will be the electrical parameters? Voltage across the switch, current through the switch, magnitude.
Current will be
0 current.
Current is 0.
Zero current and voltage?
infinite.
Infinite. Meaning infinite. Very good. The switch should be able to block. I do not know whether you are able to see my gestures. It is able to block infinite voltages, withstand. It is able to withstand infinite voltage, not voltages, voltage. Fine. And it doesn't allow any current, no leakage at all. Ideal switch, no leakage. Fine. So when the switch is off, current through the switch, I switch is 0, voltage across the switch. I should have written it. I will now write voltage across it is infinite. Ideally. Fine. Of course, current being infinity, I haven't written. So this is what switching is all about. Fine. Now, let us take this region, this characteristics. Now, if we want to on and off this switch, the BJT, where should we operate it? During on state, which region? During off state, which region? You have already answered it still.
During on state, it should be in saturation region.
Good. Saturation.
On saturation of cutoff.
Cutoff.
That's all. Then why do you have the other region?
We're working as an amplifier.
Excellent one. So if you want to work as an amplifier or make the BJT work as an amplifier, you need that active region. But what are we interested in? Switching. We don't want amplifier in power electronics. Through the switch, because power amplification is a different process, that is high gain power converter, that is a different concept. But when we want to use the device, use the BJT in discussion as a switch, we want it to be either in saturation region or in cutoff region. We don't want active region. Is this clear to you?
Yes, sir.
Yes, sir.
For everybody, or for most of you who are comfortable opening out?
Yes, sir.
Yes? Okay.
Yes, sir.
Fine. Now, let us see what is the significance of active region, or in other words, how does the saturation and cutoff region or operating the switch in saturation and cutoff is helping us in power electronics. Let us try to find that. For that, I will just point out any one operating point. Let's say if I am operating in active region, if it is just a big if. So if I am operating the switch at the point that I have indicated, what will be the voltage at that point and what will be the current at that point, meaning what will be voltage across the switch if I operate the switch here, and what will be the current flowing through the switch if I operate the switch at this operating point. That's all. I will call this as, I will name this as operating point. Can you tell what will be, will it be 0 or will it be finite? That's all. Binary.
Finite.
Finite. So I will now have this as, I will write this as VES1. I will indicate this as ISW1. We will have finite values of voltage and current if I am operating in the active region. Fine. Obviously, I can shift the operating point here, here, anywhere other than saturation and cutoff. If I operate at any other point, there will be voltage across the switch and current through the switch. Is this point clear to you?
Yes, sir.
Any doubts for anybody?
Sir, can you repeat?
I will repeat. Other than the saturation and cutoff region, if I operate the switch anywhere else in the VI characteristics, there will be finite voltage across the switch and finite current flowing through the switch. Is this point clear to you?
Yes, sir.
That's all. This is what I have been saying so far. Okay, so I will make a note of that. V switch and I switch will be finite values when the operating point active region. Is this point clear to you? So whatever I have written here, the statement, this can be understood from the characteristics. When the switch is operated in the active region, the entire thing is active region actually. Okay, because the other region is saturation and cutoff, you don't operate there. That's what we are discussing. We are trying to discuss the significance of the saturation cutoff region. So if you are operating either here or here, the entire region, so the entire region, voltage across the switch will be finite, current through the switch will be finite. This is what I have been saying so far. Now, what is the power dissipated across the switch? When VSW and ISW, they are finite, what can you say about power across the switch? I will indicate this as PSW. What will be PSW? Power across the switch. How can you find out?
VSW into ISW.
VSW into ISW. It won't be zero because VSW and ISW are finite. Therefore, power across the switch will not be zero. Fine. Did you understand this? Will also be finite, and it will be high as well. Okay. Now this is what happens when we operate in the active region. Is this preferable? Can you afford to have finite power dissipated across the switch? Is this preferable?
No, sir.
No. Why? It is not preferable. That is the correct answer. But why?
Loss of energy.
Loss. That's all. What loss?
Of
power loss. During what process?
Switching.
During?
Transferring the current or
yeah, during power conversion process. Transferring current, transferring voltage, both put together, it is going to be power conversion process. So during power conversion, during power transfer from the input side to the output side, in between we have a switch. So it is like this. We will have an input port, we will have a switch, we will have an output port. This is what we have. So in between, if we have power dissipated across the switch, then what will happen to efficiency? That's all. Okay, so obviously power dissipated across the switch should be as minimum as possible for efficiency being as high as possible. Ideally, what should be PSW? Ideally.
Zero.
Zero.
Good. This is why somebody was saying power dissipated across the switch should be zero. This is what is expected. Ideally, PSW should be zero. Should be zero. It is not equal to zero. It is should be zero. This is the most preferred way of processing electrical power. Don't have any power dissipation across the switch, across the intermediate element. It could be anything. It could be inductor, resistor, transformer, not resistor. Resistor doesn't allow that. That is why we don't use that resistor. So we are trying to use switch, inductor, capacitor. Inductor and capacitor, they don't consume real power. Therefore, yes, they get a tick mark. Switch, if power dissipation should be zero, now take the characteristics. Where should we operate the switch if power dissipation should be zero?
Saturation region and cutoff region.
Excellent. So did everybody understand this? This is the concluding part towards the end of today's session. If
Yes, sir.
yes, excellent. I'll repeat for the benefit of others. If power dissipated across the switch needs to be 0, the user must operate the switch either in cutoff or in saturation. Cutoff refers to off state, saturation refers to on state. That's all. So in power electronics, active region is dash. Please fill up that blank. In power electronics, active region is dash.
Useless.
Active region. Please, conclusion.
Not used.
Not used, avoided, not preferred, should be avoided. These are the phrases, terms that should fill that blank. Okay, this is the essence of a switch. So please remember this. In power electronics, concluding remark, better to write. I will write this. In power electronic, I will write converters also. In power electronic converters, the switch, rather than writing in a negative way, I will write in the actual regions. The switch is operated either in cut off, which means the switch is in off state, or saturation, on state. Regions only. Right. All these words, all these terms are important. Obviously, they are not in the book, my own words, but if you take out any one word, if you replace that by another word, entire meaning gets lost. Okay, but don't worry, I will give you a PDF of this. I'll circulate the PPT, everything. You can use that. Please understand, put it in your brain. That's more important. In power electronic converters, the switch is operated either in cutoff, off state, or in saturation, on state. That's all. Active region should not be thought about. Don't use the switch in active region at all. Fine. This is one major inference, one major concluding remark, one major understanding agenda of today's session. Secondly, what are the ideal characteristics of the switch? We have discussed. Of course, I had indicated them then and there as well. Voltage across the switch during on state should be 0. Voltage across the switch during off state should be infinity. Ideal switch, therefore infinity. Current through the switch during on state should be infinity. Current through the switch during current through the switch should be 0 during off state. These are the properties of an ideal lossless switch. Only then you will get VSW into ISW, which is power across a switch, equal to 0. That is the property of an ideal switch. These are the properties of an ideal switch. That's all. On that note, I'll stop. I'll pass for some time.